So, now let us start off on a new topic which has got to do with the scaling of the MOSFETs, and this is of particular interest as it is the symbol, or it is very symbolic of the advancement of your semiconductor technology. So, it is quite famous, particularly in the form of Moore's law, although surprisingly I have never referred to that here, okay, which basically says, which defines a pathway or a roadmap to scaling, which says that the number of transistors in any system or in any chip doubles every so many years. Okay. But just to give you an example, so what is scaling essentially? Before we start talking about scaling, what does scaling mean? So, we have a MOSFET here which is drawn in a very simple manner. That is your source, that is the drain, and that is the gate, and that is the insulator. It has got some thickness TOX, there is a channel length between source and drain, and the MOSFET has got some channel width. So, what do you mean by scaling? Scaling simply means reducing the dimensions. Okay. So, what we want to do is, when we say we are going to scale the MOSFET down by a factor of alpha, what we mean is we are going to reduce the channel length by a factor of alpha, we are going to reduce the channel width by a factor of alpha, and we are going to reduce the thickness by a factor of alpha. So, that is what scaling implies. And why do we need to do scaling? So that you can make the transistor smaller, and so that you can have more transistors in a given layout area, and by scaling down the transistor you improve the speed and the performance, and I mean the speed and performance and the power, you change the power consumption depending on how you scale, of course, and we will look at that. And most importantly, you can fit in a larger number of transistors in a given layout area. So, there are lots of benefits, these kind of benefits to scaling, and that is what has led to the microprocessors in the computers becoming faster, and it has led to mobile technology, etc., etc. So, it is quite an important feature of any technology as to how rapidly and how effectively you can scale down to improve performance. So, just to give you an example, I hope I am right on all these, but if I am not, I would probably correct it. But in the 1970s, so the Intel 4004 processor had about 2000 transistors in it, okay. And in 2015, that is what 45 years, okay. So, in half a century's time, the number of transistors has increased to these many, okay. That is a massive increase. And in the 1970s, so going back to the 1970s, that is the number of transistors. The transistors had a typical channel length of 10 microns, and in 2015 the channel length of the transistor is about 40 nanometers, okay. So, that is going by 3 orders of magnitude lower in terms of channel lengths. So, these kind of advancements are possible by scaling down MOSFETs in a reliable manner. So, what we are going to do here is we are going to look at what scaling is, introduce it, talk about 2 different kinds of scaling strategies and what its effect is, okay. And some of the key features and the parasitics that rise along with scaling, that come along with scaling, etc. So, firstly, how do we scale down? Okay. So, as I told you, you reduce L, W and TOX by a factor of alpha, okay, or K, it does not matter. So, there are 2 strategies. One is something called as constant field scaling, and the other is something called as constant voltage scaling, and of course, you can have a hybrid of these 2, but we will just introduce these 2 strategies. In the case of constant field scaling, the electric fields inside the device are kept constant, okay. And what does that mean? So, let us say we have scaled down the MOSFET from L to L by alpha. So, there was a certain electric field in this MOSFET, okay. So, there was a gate field, there is a source to drain field, etc. And we want to keep the magnitude of these field strengths the same, even though the transistors have been made smaller. And how do we achieve that? We achieve that by simultaneously scaling down the voltages. Okay. So, you want to keep the fields the same, and therefore, the voltages have to go down along with your dimensions. The other idea is something called as constant voltage scaling, okay, which in this case, even despite your scaling down of lengths, the voltages remain constant in order for you to continue having compatibility with regards to the power supply required for operation, etc. And obviously, in this case the electric fields are going to increase as you scale down the MOSFETs. So, we have a quick table here. So, I have just prepared an easy table for us to see as to what happens when you use constant field scaling and constant voltage scaling. So, here we are scaling down by a factor of k. Okay. So, let us say we say k is equal to 4, what that means is my channel, and let us say my initial channel length was 8 microns. What that means is if I scale down by a factor of 4, my new channel length has become 2 microns, okay, and my new channel width has become the old channel width by 4, the new Tox has become the old Tox by 4, etc., etc. Okay. So, that is what scaling down by a factor of k implies. Now, how does it affect some of the simple parameters? Okay. Channel width of course goes down by a factor of k whether it is constant voltage or constant field. Channel length goes down by a factor of k whether it is constant voltage or constant field. Oxide thickness goes down by a factor of k whether it is channel length or whether it is constant field or constant voltage. The area is basically your W into L essentially. Of course, there are a lot more things to the area because you have to have your pads, you have to have your interconnects, but to first order the size of the transistor, if you are familiar with transistor layout, then you have a certain channel length, you have a certain channel width, and therefore, the area simply scales as W over L, plus of course, there are many other aspects to the area. So, that will go down as 1 by k square since both my W and L reduced by a factor of k. So, that is area. And the electric field, in constant field scaling, the electric field is not supposed to change, that is the whole idea. So, that does not scale and remains constant at 1. And if you want to keep the electric field constant, you have to reduce your voltage, and the electric field is essentially the voltages divided by all the lengths. Okay. And since the lengths have scaled down by a factor of k, we also need to scale down the voltages by a factor of k. So, the voltage in the case of constant field scaling will scale down by a factor of k. On the other hand, the voltage in a constant voltage scaling case will not change, it has to be constant, and therefore, the electric fields all increase by a factor of k. So, what about the insulator capacitance per unit area? So, that is Cox, that is the capacitance per unit area, is nothing but epsilon ox by Tox, and our Tox scaled down by a factor of k, and therefore, the insulator capacitance per unit area has to increase by a factor of k, and that is true whether it is constant field or constant voltage scaling. Now, what about the total gate capacitance, and what do you mean by the total gate capacitance? So, this is the insulator capacitance per unit area, and therefore, the gate capacitance is the total capacitance. So, Cox into WL, which is the area of the device. So, since Cox increased by a factor of k, okay, and W decreased by a factor of k and L decreased by a factor of k, irrespective of whether it is constant voltage or constant field scaling, the total gate capacitance reduces by a factor of k. What about the current in the devices? Now, whether it is in linear mode or saturation mode, the current has a square dependence on the voltage. So, if it is in linear, you say it is mu Cox W over L. So, let me write this properly. So, in the case of linear, we say that it is mu Cox W over L into VGS minus VT minus VDS by 2 into VDS. So, that is the current. Okay. So, you can see that there is a voltage into voltage term. So, that is a V square term, V square, the voltage square dependence, and in saturation of course it's mu Cox W over L by 2 into Vgs minus Vt the whole square. So, again it is a voltage square dependence. Okay. So, what happens if you scale down? So, what are the parameters here that scale? The mobility not so much, W and L scale, but W divided by L does not scale, that is the aspect ratio. Since W scales by K and L scales down by K, W over L does not scale. Cox does scale. So, Cox, how does Cox scale in the case of constant field scaling? Cox increases by a factor of K. So, Cox becomes K times Cox. And how does voltage change in case of constant field scaling? The voltage reduces, has to reduce by a factor of K, and therefore, in the case of constant field scaling the voltage reduces by a factor of K, and therefore, in the case of constant field scaling. So, whether it is here or here it is the same. So, in the case of constant field scaling the current has to reduce by a factor of K. So, you can see it is V square by K square into K Cox, and therefore, the current reduces by a factor of K. On the other hand, in the case of constant voltage scaling, so let us just write, let us just keep things simple, we will just write the current, this current scalable, the scaling aspects of the current is dependent on Cox into V square, because the rest of the parameters do not change. So, in the case of constant voltage scaling V does not scale, so that remains 1, whereas Cox has increased by a factor of K. So, therefore, the current increases by a factor of K. Okay. So, you can see that in the constant field scaling case the current in the transistor decreases by a factor of K. In the constant voltage scaling case the current in the transistor increases by a factor of K. And what about power consumption? Power is nothing but your current into voltage, okay, IV. And since all the voltage is reduced by a factor of K in constant field scaling and the current reduced by a factor of K, the power reduces by a factor of K square. Whereas in the case of constant voltage scaling the current increased by a factor of K, the voltage remained invariant, and therefore, the product scales up by a factor of K. So, here the power increases, here the power comes down, okay. Here the current increases, here the current comes down. So, this is how you handle scaling relations. Of course, there are many other parameters one can consider, delay, etc., but we have just talked about some of the basic or the key parameters. So, what is the impact of scaling? Okay. So, the first impact of scaling down is got to do with the threshold voltage. Okay. So, we will talk about this first. So, is the threshold voltage influenced by scaling of the MOSFET? Okay. So, what we are going to do is we are going to start with a regular long channel device. So, it is a long channel device, and then we are going to head towards a short channel device, which is the scaled down version, short channel device, and we are going to see what as to what happens to the insulator. So, before we head there, how could the threshold, we are going to see what happens to the threshold voltage, sorry. I mean I am probably getting too used to saying these terms, and I am making mistakes, but nevertheless let us just carry on. So, we have the threshold voltage, and what does the threshold voltage depend on? So, once again let me repeat, it has got these 3 milestones. You need to first get your flat band voltage, which you now know that it depends on phi ms plus any trapped charge in the insulator. Okay. Then you have to have your Q depletion by Cox, okay, and this depends on the varying XD, it depends on the body to source voltage, etc. and then you need to achieve your 2 phi f. Okay. But here again it depends on the body to source voltage, which is your phi s has to be equal to 2 phi f. So, this is when you hit threshold voltage. Okay. Now, let us look at this depletion term. So, what exactly are we depleting in a MOSFET? So, here you already have an NP junction. So, this is a P type body. So, you have an N type source, an N type drain, and you have a P type body, and you already have a depletion layer here because of this diode. Okay. So, this region is already depleted for you. The gate has to deplete this region of the semiconductor. Okay. What about this region here? That region is shared between the gate and the PN junction. So, this PN junction at equilibrium will help the gate in depleting that. So, let us say half of that region is depleted by the PN junction and the remaining half is the job of the gate. So, the gate gets some help in that region. In these regions it is only the PN junction, and that region is only the gate, and in this region the PN junction helps the gate deplete. But in a long channel device, okay, so let me just write this down neatly in case my. So, this is the job of the gate needs to deplete this region. Half of this region is also the job of the gate, because this region is shared between the PN junction and the gate, and everything else, the remainder half and all these regions are all depleted by this PN junction between source and drain and bulk. So, all these are jobs of the PN junction. So, the gate essentially all the gate charge goes into deplete that particular region. Now, if it is a long channel device, these regions here are a negligible portion of the entire area the gate has to deplete. So, yes, if you have a very long channel device and you reduce the channel length by 5%, the gate is not going to see too much of in effect. Okay. So, what do you mean by long channel device? Firstly, long channel device implies that the distance between these channels, okay, the channel length, sorry, the distance between these two electrodes, the channel length is much larger as compared to all these depletion regions, much larger than these. Okay. And in that case, it really does not make too much of a difference whether the gate depleted that much or whether it depleted this much, okay, because this portion is a small percentage of the entire channel area. Okay. So, the gate can be said to be depleting the entire area, which is about W into L. Okay. So, that is the area that the gate has to deplete. Now, what happens if you start reducing the device? Okay. If you start reducing the device, okay, so here I had a nice picture and I did not use it. This dark region shows the portion of the portion depleted by the PN junction, whereas the gray region shows the portion depleted by the gate. Now, if you start scaling down the channel length, so now the channel length is reduced quite a bit. Okay. So, now these depletion regions are not that small, we cannot really ignore them, they have gotten very close to each other. So, now this region suddenly forms a significant part of the total depletion charge, right. And now we need to start taking into account this area quite carefully in order to calculate all our make calculations on the threshold voltage. Okay. And since the source, this PN junction now takes up a larger percentage or the larger share of the workload in trying to deplete, the gate has to do a smaller job, and therefore, the gate depletes that region faster at a lower VGS as compared to the long channel device. So, in other words, as we reduce the channel length, the PN junctions between, that is between the source drain and body, the PN junctions, okay, it's in fact the other way, it's the body and source or drain. Okay, since we are talking about NMOS, we are always discussing the N MOSFET, we have never discussed the P MOSFET so far. The PN junction helps the gate significantly, okay, so that is the key, significantly, and it depletes, it performs half of the workload, it depletes, it helps the gate deplete a lot of the semiconductor, and therefore the gate can, a smaller gate voltage depletes the remainder portion of the semiconductor and takes the semiconductor to threshold, and threshold voltage is reached faster. So, in other words, you need to add a lot less charge on the gate in order to completely deplete this entire region and head towards inversion. Okay, so, therefore, as the channel length reduces, the threshold voltage reduces. And if you want to see this mathematically, we just take the small analysis here. So, let us just take the depletion region of the gate, the region of the semiconductor depleted by the gate. So, that is where your source drain would be, and that is how the depletion region would be around your source drain, and this part of it is all taken care, is all depleted by the source and drain, and it is only this region here that is depleted by the gate, and that is the insulator. Okay, so, that is the picture. Now, what is this area? You know, how much of this volume is this gate depleting? What is the total depletion charge? What is the total amount of charge I must add to the gate in order for me to get a total depletion charge over here, and by total I mean in coulombs. So, we are not talking about per unit area or per unit volume, total implies in coulombs. Okay. So, not per area or volume, not this. So, what is the total charge? So, let us take a difference. Let us say what is the threshold voltage of the long channel device minus the threshold voltage of the short channel device. In the case of a long channel device, okay, this, it is almost, the total charge is almost, it is going to be Q NA XD, that is a charge per unit area, into the total area, which is all, L has not changed too much, it is only a small percentage of the L that has changed. We can also be more accurate, let us also do that, but let us just finish this first. In the case of a short channel device, these differences, you have this trapezium here, and with one side as being L dash and the other side as being L. Now, L dash is significantly less than L, whereas in a long channel device L dash was almost the same as L. So, that is the key difference. Now, since L dash is much less than L, because a larger percentage of this region is depleted by the PN junction, or this region forms a larger percentage of the total length here, you have the area to be considered is the area of the trapezium. So, that Q NA XD into W L plus L dash by 2, that is the area of the trapezium divided by I mean L plus L dash by 2 is basically your total charge in the depletion region in a short channel device. So, what is the difference between the VT of a long channel device and a short channel device? It is a difference in this depletion charge minus this depletion charge divided by the total capacitance. So, it is capacitance per unit area into WL, okay, and this minus sign is there because of, this minus sign is present because of all the charges being negative. So, this total depletion charge is Q Na by Cox into WL XD divided by WL. So, that is this term, and Q total depletion in the short channel device divided by the total gate capacitance is given by this term. So, essentially this reduces to an expression of this kind, and if L dash is less than L, this term is greater than 0, which means the Vt of the long channel device is greater than the Vt of the short channel device, or in other words, if you reduce the channel length, the Vt reduces. Okay. Now, if you want to be more accurate, let us just go through that exercise as well, although it is not written here, we will just work it out. Let us say that you want to consider this trapezium even in a long channel device. Okay, that is true, because although here the trapezium is more pronounced, it also does exist in a long channel device. It is just that these regions are a much smaller percentage of the total length, total channel length, and that is the primary difference, right. So, what is, let's call this as L double dash and capital L, okay. And what is the depletion charge in this device? It will basically be your Q Na, I am just taking the magnitude, Q Na XD into W into the area of this trapezium, which will be L plus L double dash by 2, okay, and that divided by the total gate capacitance is essentially going to be, let us get rid of the W's, it is essentially going to give you Q Na XD by Cox into 1 plus, let us say 2 Cox, 1 plus L double dash by L. So, that is the Q depletion of the long channel device in an accurate manner, accurately. Okay. So, L, say L is 10 microns, and this is say of the order of 1 or 0.1 microns, and therefore, L double dash is 9.8 microns. So, this number here is basically 0.98. Okay. Whereas, if my L was much smaller, okay, so if on the other hand, if my L approaches say 1 micron, and this still remains to be 0.1 micron because this doping concentration has not changed, and my L dash for a short channel device approaches 1 minus 0.2, which is 0.8 micron. Then my L dash by L is a smaller number, and therefore, it is going to have a larger impact. And further, if we further reduce L, so let us say we make L as 0.4 microns as we are beginning to approach the depletion thicknesses, then my L dash would now become 0.2 microns. So, it will be L minus 0.2 because each of these regions is 0.1, and therefore, my L dash by L has now become half. So, much more significant. So, you can see that as L decreases, the impact of this term begins to show up to a greater extent, okay, and therefore, the threshold voltage starts becoming smaller and smaller as my L decreases. So, now what about the impact of scaling on the channel width? Okay. So, we have the MOSFET, which has got which is the gate, insulator, semiconductor, and you now have we have discussed the impact of channel length, but what about reducing channel width? Okay. So, for reducing channel length we say it is a long channel device to a short channel device, but for channel width we say it is a wide device to a narrow device. Now, let us take the cross section of a wide device. Okay. We are going to look at this device from this side. Okay. We have always been looking at the device inside the plane, we have always looked at this cross section, but now let us start looking at that cross section. Okay. So, that cross section is shown here. Okay. So, here I have taken a cross section right in the center of the device. So, you can't see the source and drain, we have bypassed it, we are somewhere in the middle of the channel. Okay. And you have your gate metal, you have the insulator, that is the semiconductor, and that is the depletion region, and you have oxides on all these sides, okay, on the side walls. It is all insulator, and the source is somewhere outside the screen and the drain is somewhere inside the screen. Okay. So, we are looking the channel lies in and out of this plane. So, we are looking through the device in this direction, and therefore, this is the channel width of the device, or this is the intended channel width of the device. Now, what is the impact of reducing this channel width as we scale down? Impact of reducing the channel width on the threshold voltage of the MOSFET. Okay. So, if the channel width, so let us look at the depletion profile. So, once again the answer has got to do with the depletion charge, the total depletion charge. So, if you look at this depletion profile, yes, most of this depletion, if you look at the total depletion charge, all this depletion charge spans over a length of W, and of course, the channel length is say L, and therefore, W into L is what is depleted. But then because of the fringing in the field, okay, so you do have some field lines, okay, heading towards the sides, and therefore, due to this fringing of the field you are going to end up, whether you like it or not, we are going to end up depleting some excess charge on the sides, and this excess charge is not really contributing too much to the behavior of the MOSFET, but it is simply that if you add some charge on the gate, you are going to end up not only depleting this region, but you are also going to unintentionally deplete the regions on the sides because of the fringing of the fields. Now, for a very wide device, this extra work done really does not make any difference. Okay. It is a very small percentage of this total channel width. So, this W dash is a very small percentage of W. Okay. But for a short channel device, it becomes a very significant portion. Okay. So, let us say if let us say we intended to add some positive charge on the gate and quickly deplete this region, and after that when we add some more extra charge we expect inversion, okay, or the definition of VT. But now since the extra charge, so now since whatever charge is being added there is also compensated for by these regions on the sides, right. So, I still need to add more charge, and once again that is also compensated for this, and only when you add a lot more charge will the depletion region finally be fully depleted and then allow inversion. So, you need to add a lot more charge on the gate because these regions on the sides are helping helping the semiconductor respond to this applied charge, and therefore, you need to do a lot more work before you get inversion, and therefore, reducing the channel width increases the VT. Okay. And it is again a percentage question, right. So, this is my channel width W, these regions have now become significant compared to this W, and therefore, the VT actually increases. Okay. And if you want to see the mathematics of it, you can say that, let us say what is the difference between a wide channel device and a narrow channel device. The wide channel device has got what is the total depletion charge. Again we are going to measure the charge in coulombs and not per unit area or volume. The total depletion charge in a wide channel device, the total depletion charge is your Q NA XD into W into L. and that divided by the total gate capacitance is nothing but Cox into WL. What is the total depletion charge in a narrow channel device? Now the side regions cannot be ignored. Okay. So even here the side regions are present, but W plus anything on the side is approximately W. This excess charge is very minuscule compared to the total charge in the gate, but now it is not. Okay, so in this case it is going to be Q Na XD by Cox WL into W LXD, which is this region, which is your regular, which is the regular region that you have already, that you need to deplete, but we are now depleting some extra regions. Okay, and we are going to model it, model this extra region not like these little triangles, but model it along these fringing lines, the fringing electric field. Okay, so that's, it's going to have a more of a circular profile. So you are going to have these circular arcs. So although I have shown it as straight edges just for this, just because it is easier to draw, you have a gate, you have an insulator here, and this insulator is a sharp, if you look at this edge of this insulator, it is a sharp corner, and this corner is going to have a very strong fringing field. So that is the way the field lines are going to be present. It is going to have a very strong field, and therefore this is the depletion region. It's you can say it's more like a sector of a circle, and then here you have this region that's depleted. So that corresponds to this, and this corresponds to this. So if you take that little accuracy, if you bring in that little accuracy in the picture, you will find that we use the area of that little sector to define this excess area being depleted. That divided by WL, that divided by Cox into WL is this term. So what is the difference between these two terms? The difference will now be a negative number, which implies that my threshold voltage for the wide channel device is going to be less than the threshold voltage for a narrow channel device. So in summary, as we scaled down L, the Vt also decreased. Okay, so the transistor is turning on faster, and why is that? Because the PN junction is helping, is aiding the depletion. But if you scale down W, the Vt increases, and why is that? It is because you have to do some extra work in depleting some regions on the sides of the channel. Okay, so I hope this qualitative and quantitative explanation helps out, but if there are any questions, do feel free to send me an email.